Imagine two lamps connected by a strange machine. One lamp seems ordinary. The other behaves in a way that depends entirely on the first. This machine follows only one rule. If the first lamp is off, nothing happens. But if the first lamp is on, the second lamp instantly changes its state.
In classical computing, this idea resembles a controlled operation. One bit decides whether another bit should change. Quantum computers take this concept much further. Instead of ordinary bits, they use qubits that may exist in multiple possibilities simultaneously. The quantum version of this machine is called the controlled NOT gate, or simply the CNOT gate. The filled circle represents the control qubit. The plus sign marks the target qubit. Together, they create one of the most important gates in quantum computing. If the control qubit is 0, the target remains untouched. Even if the target starts as 1, a 0 control qubit still prevents any change. But when the control qubit becomes 1, the target qubit flips instantly. A target qubit that was already 1 becomes 0. The gate behaves exactly like a quantum switch. These four possibilities completely describe how the CNOT gate behaves on ordinary computational states. But quantum mechanics allows something much stranger. The control qubit itself can be in a superposition. Suppose the control qubit is simultaneously 0 and 1.
The CNOT gate now acts on both possibilities at the same time.
Something extraordinary emerges. The two qubits become entangled.
Measuring one qubit instantly tells us the state of the other, no matter how we choose to observe them.
Imagine two spinning coins sharing a mysterious connection. Once one decides, the other somehow already knows. Einstein famously called this phenomenon spooky action at a distance. The CNOT gate is much more than a curiosity. It is one of the fundamental building blocks of quantum computation. Quantum teleportation, error correction, and powerful algorithms all rely heavily on CNOT operations. In fact, combining Hadamard gates with CNOT gates allows us to build almost any quantum circuit imaginable. Modern quantum computers spend enormous engineering effort trying to perform CNOT gates with extreme precision. Even tiny imperfections can destroy entanglement, making reliable CNOT operations one of the greatest technological challenges. The CNOT gate does something no single qubit gate can accomplish. It creates genuine relationships between quantum systems.
A single qubit dances alone. But CNOT teaches qubits how to dance together.
Through entanglement, information is no longer stored separately. It becomes woven into a larger quantum fabric. The mysterious machine on the wooden table was never about lamps. It was teaching us one of nature's deepest secrets.
The CNOT gate transforms independent qubits into partners, sharing a connection unlike anything found in classical physics. Every large-scale quantum algorithm depends on gates like CNOT, turning fragile quantum possibilities into meaningful computations. In the quantum world, computation is not only about changing states. Sometimes, the greatest power comes from creating connections that simply cannot exist anywhere else.